Hi everyone, my name is Hao Zheng. Our group is final project is an agent AI based on game theory and heuristic search. Before I officially introduce our project, I'd like to ask my two teammates to talk a little about their work on MCTS.
Hi everyone, our first AI method is based on the classic Monte Carlo tree search, but we have made it smarter by adding adaptive turning and strategy improvements. We use the UCT rules to pick moves during the search, but instead of using a fixed exploration constant, we change it over time from 1.7 down to 1.41. This helps the agent explore more in the early game and focus more in the late game. When expanding the tree, we don't add all possible moves. We use a constant heuristic to add only the best one. This saves time and keeps the search focused on good options. To stay safe on the time limits, we have a fallback. If MCTS runs too long, we switch to a greedy moves instantly. So overall, this method builds on base MCTS but adds smart turning and heuristic thinking, making our agents both strategy and fast.
My teammate, our maze both extend MCTS, but mine focus on adaptive skill switching, reacting to board pressure dynamically using a critic score. In contrast, my teammates approach the use of fixed heuristic evaluation, focus on stable, greedy guided routes. My maze is more reactive and stronger under threat, while theirs is efficiency but
Alright, now I will introduce our final project, an AI based on game theory and heuristic search. Firstly, let me explain the game theory method I used. Minimax strategy. In my code, minimax is mainly used to lead the agent priority situation where it can win immediately or the enemy is about to win. One example is when the agent sees a spot that can complete a sequence, it will occupy that spot immediately. Another case is related to the hotbox situation when capturing all 4 points lead to a win, the middle spot becomes the top priority. Threats analysis. This part is about creating threats or breaking the enemy threats. This means removing the middle point of long sequence of the enemy or breaking shared point between two sequences by removing the common one. Zero-sum game. This is the most important concept in our project. With the help of rule base and the heuristic function, we can just figure out the card we really want, and actually we can also guess which card the enemy wants. Then, even if we don't need the card, we can still drift it just to block the enemy. In our test, adding this zero-sum idea boosted the agent's win rate by 30% compared to the version without it. Besides what I just mentioned, my code also uses many other decision rules based on game theory that I can't talk too much about it because the time limit of the video. Okay, now we have two selector, action selector and drift card selector. For drift card selector, which help pick the card that action selector wants the most. I mean, like the card that will make the agent win the game immediately. But what if, based on the rules we designed via game theory, we still can't find out which card we need to get? How can we get the best card we needed now? To solve this, I designed a heuristic search function. When the action selector doesn't get a clear favor card, maybe because it's just at the beginning of the game, we score each card based on its position, based on how many connections it can help make. Then we choose the one that the highest scores. That high scores card is the most benefits card for us. About the future, I think my code will have 2 points to develop. The first one is to guess enemy card based on your hand card, based on drift card, based on board. And the second one is to use Bayes models to figure out the enemy type. If it's aggressive, it is defensive, is it balanced, we can adjust our strategy depending on it. In the end, the game theory based code performed really good. It bet all kinds of AIs in my group, including my DQN and my team's MCTS. Okay, thank you. Thank you for listening.